Imagine a remote research station in the dead of an Antarctic winter, or a disaster-stricken city where the grid has simply vanished. Traditionally, keeping the lights on meant a never-ending, expensive, and carbon-heavy chain of diesel trucks. But the WardZero system, announced in March 2026, changes the math entirely. It is a fully functional nuclear reactor designed to fit inside a standard ISO shipping container, capable of being deployed anywhere on Earth. This isn't just a smaller version of the massive plants we see today. It's a fundamental reimagining of nuclear engineering, built around the idea that the reactor should go to the power, not the other way around. To make a reactor this small and portable, engineers had to solve three massive challenges: how to keep the fuel safe without a giant containment dome, how to cool it without a river, and how to make it survive a plane crash. The solution starts at the microscopic level. Instead of the long metal fuel rods used in traditional reactors, WardZero uses millions of tiny, indestructible pebbles, known as TRISO particles. Each of these particles is its own containment vessel, engineered to withstand temperatures that would melt most industrial metals. It's the ultimate defense-in-depth strategy, shrunk down to the size of a grain of sand. The secret to this fuel is the silicon carbide layer. It's a ceramic material so tough that it acts as a pressure vessel, trapping radioactive fission products inside even at temperatures exceeding 750 degrees Celsius. This means that even if the reactor loses all its coolant, the fuel won't melt. It's physically impossible for the radioactive material to leak out because the containment is baked into the fuel itself. By eliminating the need for a massive concrete containment building, the WardZero team could focus on the next big hurdle, the cooling system. And for a transportable reactor, water was out of the question. Traditional reactors need millions of gallons of water to stay cool, which is why they're always built near rivers or oceans. But WardZero uses a plug-and-play gas cooling architecture using an inert gas mixture. This gas circulates through the core, picks up the heat from the TRISO pebbles, and carries it to a heat exchanger. Because gas doesn't boil like water, the system can operate at much higher, more efficient temperatures. This high-temperature heat isn't just for making electricity. It's industrial process heat, which is incredibly valuable for things like hydrogen production, water desalination, or chemical manufacturing. But the most impressive feat of engineering might be how this system handles the journey. To be truly transportable, it has to be safe while moving at 500 miles per hour inside a C-17 cargo plane. This required a concept called kinetic hardening. Engineers designed the internal structure to ensure that even in a high-impact crash, the reactor remains subcritical and the fuel stays contained. It's a masterclass in mechanical resilience. Every component, from the core supports to the gas lines, is built to withstand forces that would shred a normal industrial machine. Let's look at how they did it. To understand why WardZero is so stable, we have to look at the geometry of the core. Unlike a large reactor that needs active pumps to prevent a meltdown, this core is designed for passive safety. The core's surface area to volume ratio is carefully tuned. If the reactor gets too hot, the physics of the materials themselves naturally slow down the nuclear reaction, a property called a negative temperature coefficient. It's like a car that automatically applies the brakes if it starts going too fast. No computer or human operator is required. The laws of physics do the work for you. Now, let's talk about that silicon carbide layer again. In the engineering world, SiC is legendary for its hardness and thermal conductivity. It's the same material used in high-performance ceramic brakes for supercars. In the WardZero, this layer acts as a tiny individual pressure vessel for every single grain of fuel. It's designed to hold in the pressure of the fission gases even at extreme temperatures and radiation levels. Even if you crushed the entire reactor container, you would still have to break millions of these microscopic ceramic armor shells to release any radioactive material. That is the power of TRISO. The gas cooling system is the second pillar of this engineering marvel. By using a mixture of helium and nitrogen, the reactor can operate at 750 degrees Celsius without the high pressures required by water-cooled systems. This gas is circulated by high-speed electromagnetic bearings. Because there's no physical contact between the spinning parts and the housing, there's no friction, no wear, and no need for oil lubrication. This means the cooling system can run for years with zero maintenance, a critical requirement for a reactor that might deploy to a remote island or a military base for a decade at a time. But what happens if the power goes out? In a traditional plant, you need backup generators to keep the pumps running. In the WardZero, the system is designed to use natural convection. As the gas heats up, it naturally rises, carrying heat away from the core and dissipating it through the container's skin to the outside air. It's a cooling system that works even if every battery and motor fails. This walk-away safety is the holy grail of nuclear engineering. It means that in an emergency, the operators don't need to do anything. The reactor simply cools itself down and shuts itself off. Finally, we have to address the kinetic part of the engineering. When you're transporting a reactor, the biggest risk isn't a meltdown, it's a physical impact. A truck crash, a train derailment, or a hard landing. The WardZero's internal structure is a masterwork of shock absorption. The core is suspended in a specialized lattice that deforms to absorb energy, much like the crumple zones in a modern car. This ensures that even if the container is dropped from a significant height, the fuel pebbles stay in their precise geometry, preventing the reactor from ever accidentally starting back up. The true genius of the WardZero isn't just that it's safe, it's how it's deployed. It's designed to be plug-and-play. Once the container arrives at its destination, it can be operational in less than 72 hours. The interface is standardized. It provides high-voltage electricity, but it also has a secondary loop that delivers that 750-degree process heat directly to industrial equipment. This dual-output design makes it a Swiss Army knife for energy. It can power a small city while simultaneously desalinating water or creating carbon-neutral jet fuel. Think about the implications for heavy industry. Right now, factories that need high-grade heat, like steel or cement plants, have to burn fossil fuels. There's no electric heater that can efficiently do the job at this scale. But a fleet of WardZero reactors could provide that heat directly with zero emissions. It's a way to decarbonize the hard-to-abate sectors that batteries and solar panels simply can't reach. By moving the heat source right next to the factory, we also eliminate the massive energy losses that happen when you try to transport electricity over long distances. When the fuel is finally spent, after 7 to 10 years of continuous operation, the entire container is simply shipped back to a central facility. There is no on-site refueling and no radioactive waste left behind. The TRISO pebbles are removed, the core is inspected, and the container is refurbished for its next mission. It's a nuclear-as-a-service model that treats a reactor like a giant rechargeable battery. This eliminates the biggest headache for potential users, the complexity of managing a nuclear site. The customer just pays for the energy. The engineering team handles the rest. The WardZero represents a shift in how we think about nuclear energy. It moves us away from mega projects that take decades to build and toward mass-produced, factory-built hardware. By building these in a controlled factory environment, every unit is identical, every weld is perfect, and the cost per unit drops significantly. It's the same way we build airplanes or cars. This scalability is what makes it a world-changing technology. We don't need one perfect reactor. We need 10,000 reliable ones deployed to every corner of the globe. Next time you see a shipping container on a truck or a ship, think about the incredible engineering hidden inside the WardZero. It's a reminder that the most complex problems often have the most elegant, compact solutions. From the microscopic armor of TRISO fuel to the crash-proof kinetic hardening, it is a triumph of mechanical and thermal design. It's not just a reactor, it's a promise of clean, portable power for everyone. The era of the atomic shipping container has begun, and it's going to change how we power our world, one box at a time.